And finally, guys, here is the final fourth part of the notes from section 8.1. As I said, it was a pretty darn long section. We now have a second theorem here within this section. 8.1 was the Pythagorean theorem itself. 8.2 is the converse of the Pythagorean theorem, although this is actually more involved than simply the converse. Okay, so the Pythagorean theorem itself says that if triangle ABC is a right triangle, then a squared plus b squared is equal to c squared. The converse of that theorem would flip around the if and the then. And we're going to go ahead and write that, although for a reason you'll see soon, I'm going to write it a little bit backwards. So the first thing we're going to write down here is if c squared is equal to a squared plus b squared. Okay, so there's the Pythagorean theorem. Then we know that triangle ABC is a right triangle. So again, guys, just to make sure that we understand what's going on, the original Pythagorean theorem, if we wrote it in if-then form, would say if triangle ABC is a right triangle, then a squared plus b squared would equal c squared. This flips things around just a little bit. Let me stop right there for a second. There's two more things that we're going to write here. That's kind of case number one. There's going to be a second case, and there's going to be a third case. But let me stop you right here, and let's look at an example here. We're going to classify a triangle with side lengths of 11 and 60 and 61. So what we would try to do here, by the way, when we talk about classify, I didn't get to this yet, there's three different types of triangles in terms of their angles. This thing could be either acute or obtuse or right. So what we would attempt to do here, guys, is to use the Pythagorean theorem, c squared is equal to a squared plus b squared, and see if this one works out. Now, even though we don't know yet if this is a right triangle, so we really shouldn't be using the words leg and hypotenuse, if it were a right triangle, C would have to be the longest side. So the long one here, the 61, would have to go in the place of C, or this thing has no chance of working. 61 squared equals, and then the two legs would have to be 11, don't forget to square it, and 60, don't forget to square that. It doesn't matter what order you put these two numbers in, but the 61, the largest number, has to go by itself. Okay, so I'm going to go to my calculator, and on the left-hand side, I'm going to do 61 squared, and my calculator tells me that that number is 3721. On the right side, again, you can do this all at once. 11 squared plus 60 squared gets us, wouldn't you know it, 3721. So what just happened, guys? C squared was equal to a squared plus b squared. The Pythagorean theorem worked out. Therefore, we know that this triangle that we're talking about has to be a right triangle because the Pythagorean theorem held true. C squared was equal to a squared plus b squared. Hey, and incidentally, you just found a group of three numbers right there on which the Pythagorean theorem works. 11, 60, 61 is another Pythagorean triple above and beyond the 5 that I asked you guys to look at earlier. Okay, we're going to move on into another example in just a second, but for now we're going to go ahead and talk about the other two cases. So the first case was where c squared was equal to a squared plus b squared. The second case, and I'm not sure what order to present this in, but here we go. The second possibility is that c squared could be greater than a squared plus b squared. And the third case could be that c squared would be less than a squared plus b squared. Now, as you've probably guessed, the only way your triangle is going to be a right triangle is if c squared equals that sum. These other two cases here, guys, are where we get acute and obtuse triangles. So I'm going to go ahead and give you this information now. Triangle ABC is, now this right here is the reason I had you guys write it backwards. If you put the c squared at the beginning, a greater than sign right here means that triangle ABC is obtuse. And going along with that now, if c squared is less than a squared plus b squared, less than means that triangle ABC is going to be an acute triangle. And I don't know about you guys, I find it logical to think about the idea that greater than, which generally means big, gets you obtuse, and less than, which usually means something is smaller, that's going to get you an acute triangle. That's the reason I had you write it with the c squared first. To write it the other way, it would be, to me anyway, counterintuitive. If a squared plus b squared was greater than c squared, that's actually the same information we have right here. That would be acute. And with the greater than, I don't think acute, I think obtuse. So I am going to get rid of some of that junk that I just wrote there. This is the important takeaway. So now with those three things written down, let's see what's going on here in example B, where we're going to classify a triangle with side lengths of 3, 5, and 7. So again, we're going to write c squared, and we really shouldn't be putting an equal sign. I'm going to put just a blank box right there, and we're going to compare c squared to the sum of a squared and b squared. Okay, the c always represents the longest side, which is 7. So 7 squared would compare to, and now the other two, the order doesn't matter, but I usually like to let a be the smallest one, 3 squared, and b would be the middle side, which is 5 squared. Okay, left side, 7 squared is 49. That compares to, and here we go, 3 squared is 9, 5 squared is 25, so that equals 36. Now pretty clearly, everybody, 49 does not equal 36, so we know that this is not a right triangle. But we can be more specific than that. 49 is greater than 36. Which means 7 squared is greater than 3 squared plus 5 squared, which means going up to the top of the ladder now, c squared is greater than a squared plus b squared. And when c squared is greater, greater means big, that means we are dealing with an obtuse triangle with side lengths of 3, 5, and 7. Okay. One last example to finish this one up right here. Classify a triangle with sides of 5, 5, and 5. I did this on purpose. This is actually a way that still to this day, guys, when I sometimes forget or get confused about which one is which in terms of greater or less than, being obtuse or acute, this is kind of a little mental exercise you can take to go through it. All right, c squared compares somehow to a squared plus b squared. Now, the weird thing about this one is all three sides, 5, 5, and 5, are exactly the same, so it doesn't matter what you put where. 5 squared gets compared to 5 squared plus 5 squared. Okay, so on the left, 5 squared is 25. Compares to, on the right, this is another 25 plus a second 25, which is going to get you 50. What I hope you guys realize here is that no matter what the numbers are, unless we're talking about 0, which wouldn't work in a triangle anyway, this right side is always going to be greater than this left side. 25 is less than 50. Less than and less than. And when c squared is less than a squared plus b squared, that means that the triangle we're dealing with is acute, which some of you may have known 5 minutes ago. Because if you look at a triangle with side lengths of 5, 5, and 5, they're all the same. And the word for that, a triangle with all of its sides congruent, is equilateral. An equilateral triangle has 3 sides that are all the same, and in this one case, 5, 5, and 5. And something I'm hoping you guys have picked up earlier on in the year, if a triangle is equilateral, meaning it has 3 congruent sides, it also automatically must be equiangular. All 3 angles have to be congruent as well. Well, we know that the sum of the 3 angles in any triangle has to be 180. So if we took 180 and divided that by 3, that means that every angle in an equilateral triangle, which is what we're dealing with here, must be, no doubt about it, 60 degrees. Every single one of them has to be 60. Acute, 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 and that's the definition of an acute triangle. So I always think of that equilateral case to help me remember here sometimes that the less than ends up giving you an acute triangle. Whew. Okay, guys, that was a long section on 8.1. If we were doing this in class, this would probably have taken us at least 3, if not 4 days of notes to get through. So let's give the homework a try and see how you do on it.